Okay, we are recording now. Plan for today, finish up on adaptive filter, the one that we started last class. That would hopefully take 10 minutes, 15 minutes max. Then talk about an application of noise cancellation or application of adaptive filter to noise cancellation, but with IoT mixed into it. And that means, and because this course has these elements of mobile, IoT, etc., I think noise cancellation by itself is a very classical area. It's very well studied. It's difficult to make breakthroughs or bring some very new ideas into it. But once you think of things from an IoT perspective, I think there are opportunities that open up. So we will discuss that, and that should take another 40 minutes. And in the last 20, 25 minutes in the class, I'll quickly go through some information about midterm, what to expect, what kind of questions to expect, and etc. Okay, so logistics as well. On the website, I just uploaded a midterm.pdf, which is essentially what I'm going to use later. And I also have uploaded the noise IoT for noise cancellation slides. I call it pre-slides. So I hope you're able to download it. By the way, the website says dynamic time warping, alignment of speech, ECG. Sorry, that's a mistake. I shouldn't have said that. That's coming up after that's coming up for next class. But this class, we are going to do applications to active noise cancellation. But the pre-slides are for noise cancellation. Okay, good. So any questions?
Could I ask a quick question?
Yes, please.
So I understood the sort of like the math and the intuition behind what we were talking about with noise, with the adapted filtering, but I had a question about a specific sign that we chose. So we said that dk minus w transpose s equals ek. I was just wondering, like, I understand what you're going for, but I was just wondering why we chose a minus instead of a plus, because I thought usually whether interference is constructive or destructive, like usually we represent it as a plus. Is there a reason we did minus?
No. We can very much do this plus, just that the W's will then change accordingly so that DK and WTS are towards opposite directions. That's all we want.
Gotcha. Okay, so just adjust the math, basically.
Yeah.
Okay.
I was writing minus just to kind of give you the sense that, oh, these two should cancel each other.
Okay. That makes sense.
We can very much write this as plus, and DK and WTS. We want WTS, that dot product, to come out as the negative of DK. Now, if DK is negative, WTS should come out as positive so that they cancel each other.
Okay. Because I think if DK is positive and then you have a minus and then WTS is a negative, that would give you like...
No, then WT has to be positive.
Right, okay.
Basically, the control that you have is on WT, right? S is what is coming in. S is what is coming in. DK is also what is coming in directly from the source to the feedback microphone, right? So the only control you have is you're multiplying this WT is what your signal processing chip has. And what you're doing is you're multiplying WT with S, and you want WTS to be the opposite of DK.
Okay. With a plus, right? If it's plus, and then if it's
because the feedback microphone is going to get DK plus WTS.
Right. Okay. And then it cancels. Gotcha.
Right. Now the DSP, if you are the DSP, your job is to figure out what WT should be. That's the adaptive filtering part, is to figure out what WTS should be so that DK plus WTS equals 0.
Okay. Yeah. Sounds good. Okay. Thank you.
Good. Okay. Any other question? I know I went through this a little bit fast, but any other question? And I'm going to quickly kind of go through this. So if you have any questions, stop me. Okay. All we are doing is we have this vector S, which is SK minus 1. Sorry. This vector S can be thought of as a signal. Oh, by the way, guys, I'm using the last class's notes because we are almost done. So I did not upload a new pre-notes. This is the last class's pre-notes. We'll just finish this part today and we are done. So please keep that in mind. Okay, so the signal that we are getting, let me write that in blue maybe. The signal that we are getting over here is basically first comes, oh, maybe we should write it as, first comes Sk, before that came Sk minus 1, before that came Sk minus 2, and so on. Right? Or another way of writing that might be Sk minus 1 dot dot S1. Right? S1 went through first, then S2 went, then S3 went, then Sk minus 1 went, then Sk went. Right? And when Sk is going, we are also saying Dk is going. Right? Good. What is our job? Once Dk comes in and we have this Sk coming in, this is a delay. So this is Sk minus 1. This is the previous sample, right? This is Sk minus 2 and so on. And we are multiplying Sk with W1, Sk minus 1 with W2, Sk minus n minus 1 with Wn. And that is this dot product. Right? W1 times Sk plus W2 times Sk minus 1 all the way till Wn times Sk minus n minus 1. Right? So this is basically the control that you have. Anything that you can do has to do with figuring out what W1 to Wn this weight vector is. That's the only thing that you can regulate. But your job is to regulate this such that the outcome of that regulation, which is WTS, which is a dot product of two vectors, when added up, again, let's be consistent with John, what John is bringing up. Let's make, because we made this plus, let's make this plus. So you regulate W such that when WTS gets added up with DK, that added up value is EK, and that we want it to be 0. So then we can write this optimization, which is minimize expected value of EK square. Right? This EK, I want to minimize that value in expectation. Okay. So now if I want to do that, we said that anytime we see a function and we want to minimize. Oh, sorry, Lucas. Yes. That was Lucas's question. Sorry, I didn't say, I thought it was John. Okay, so anytime you want to minimize, let's differentiate. Okay, so expected value of EK square is nothing but expected value of DK. Again, this should be plus. If we do it plus, that's fine, right? We wrote that as DK minus, but we can write that as DK plus as well. Right? Just that the W's will become the other way. That's all. Okay. So DK minus WTSK, DK minus WTSK transpose. You see that? A vector square is nothing but that vector times transpose. Now this is an expectation, right? So there's an expectation outside this. So now let's expand this multiplication. Okay. So this is DK, which is DK square, or DK transpose, which is DK square, expectation of that, plus WTSK, sorry, this is not WTSK. This is WTSK transpose, right? Okay, so dk minus WTSK, dk transpose minus SK transpose W, right? Because I brought this transpose inside the brackets. Remember, we said A plus B transpose equals A transpose plus B transpose, but also AB transpose is B transpose A transpose. It flips, right? And now you basically multiply these cross terms. dk transpose becomes dk square. WTSK times SKTW becomes WT SK transpose W, but SK transpose is nothing but the covariance matrix, expectation of that. Expectation of SK transpose is the covariance matrix of S. What is a covariance matrix? What is covariance? Covariance is how two signals vary, whether they go up and down together or they go up and down at random times. Sometimes they may go up, sometimes they may go down together, sometimes they'll go in opposite ways. We don't know, right? So it's a measure of how these signals go up and down together. Okay, so that's the covariance matrix. Similarly, this term times this term gives you a covariance between S and D. Similarly, this term and this term, sorry, this term and this term gives you a covariance also between S and D, right? So it turns out the differential of this function with respect to W, because W is the thing that you can control, right? Remember we said W is these parameters that we can control, and we want to find the function and we want to differentiate this function and find which value of W will bring us to the minimum. So delta WF becomes, if you differentiate this with respect to W, that's 0. This becomes 2RSW, and this becomes 2RSD, because this W and this W, when you differentiate once, only the coefficient remains. And this is vector differentiation. So I hope you have seen vector differentiation in the past. If you have not, do look at it. Let me give you some peace that in the midterm, we're not going to ask you anything around vector differentiation. Okay? But it's good to know that. It's good to know how we got 2RSW by differentiating this with respect to W. Okay? Now this is 0, which means we want W, right? This is what we are after, because remember, right? Anything that you can do has to do with W, or rather W is the only thing that you can change. So then W equals 2RS, 2RDS, 2RS. So W star is RS inverse RDS, which means the inverse of the sources covariance matrix times the source and D covariance matrix. Source meaning the DSP's source, right? This S and this D, how do they vary? If you look at them jointly, how do they vary together? Do they go up and down together, or do they go in opposite directions? Guys, this is one thing to remember. If they go in opposite direction, that also means that their correlation is -1. If they go in the same direction, then their correlation is +1. But if there is no pattern in which they go up and down, it's neither together, neither downward. Sometimes they go up together, sometimes they go down together. Sometimes there is no, when you multiply them, if it becomes 0 in expectation, then it's uncorrelated, right? So this RSD captures this joint variation of S and D. So if you know how the S and D jointly varies, and if you know how S varies between itself, then you can find W star. Okay. And if you know W star, you exactly know what to put it at these weights, because W is a vector. So W star is the optimal vector. And then you have your adaptive filter ready. The problem is you do not know these covariances. Right? Okay, we will look at that. But one more thing I wanted to say was you optimize this by directly differentiating the function and equating to 0. Another way to do it is to take that same function, take the same function and do gradient descent on it. And remember, for gradient descent, we only need the derivative of that function, the derivative of the objective function, right? So the derivative of the objective function is this. So remember we said Wk is Wk minus 1 minus alpha. Alpha is the step size times the derivative, right? So if you know the derivative of the function, we should be able to kind of climb down that function as a hill, and we should be able to find the right W star. And if you do that, you'll also realize it comes to the same answer. Right? So one time we did it by directly differentiating in a closed form. The other way we did it was by doing gradient descent. Okay. But they both give you the same answer, understandably. But the good thing with gradient descent is that this inverting a matrix is sometimes painful. Right? So with gradient descent, you don't need to invert this matrix. So that's one advantage, slight advantage of gradient descent. But then gradient descent, you have to run the iterations multiple times before it converges. With a closed form solution, you don't have to do any of that. So there are some trade-offs. But the bottom line is, I do not know RS, I do not know RDS. Both are unknown. Right? Imagine you are the DSP. A signal is coming to you from the reference microphone. Right? Maybe you can figure out RS. Maybe, right? Because if you keep a buffer of the past, you can see how this signal is correlated over time. But this decay, you don't know, because what you're getting at the feedback microphone is the sum of your decay and your WTS that you are transmitting. Right? So you do not know that code, that the variation of this and this, the covariation of those two. So then what do you do? Right? And then the idea in the adaptive filter is that, okay, expected covariance matrix is essentially an expectation over time. Okay. But I don't have so much of information. What I'll do is I will approximate that RS and RDS with the current values of SK and DK. Meaning RS, I'm going to write as SK transpose. Remember, what was RS? Ideally, RS is nothing but expectation of SK transpose. This is perfect. But I don't have that expectation. So I would approximate this right-hand side as only SK transpose. If I had to do expectation, I should have kept a buffer of all the stuff in the past and done the expectation. Maybe this is doable, okay? But this one is definitely much harder. Because I want the expectation. This one is the expectation of SK DK. That is much harder, right? because I don't know what dk is. As a result, I'm again going to approximate that by this. Okay. And now I'm going to run. So this is an approximation. But the good thing about that is, if I do this approximation, then this becomes 2sk, 2sk comes out, and inside the bracket, it becomes sk tau w minus dk. And guess what that is? That is your ek. Okay. So now what you have? The adaptive filter is saying that your gradient is your current value of sk multiplied by what the feedback microphone is giving you at this current time. Right? Because what is ek? Ek is what the feedback microphone is telling you. Right? So you multiply these two, sk ek, and that's your gradient. And now you start doing gradient descent. You basically say wk plus 1, which is I'm climbing down the hill, right? W is basically the domain of the function. So wk plus 1, someone tell me what should I write here? Equals the previous wk, then minus my step size, alpha, and which direction should I climb down?
Opposite to the gradient?
Opposite to the gradient. What is the gradient in this case? Opposite to the gradient. So opposite, I've already captured the opposite part by this negative. So what is the gradient now?
Minus 2. Sorry, go ahead.
Oh, yeah. I think like he was going to say, I think it's the 2sk-ek. Yep, the minus 2sk-ek.
Correct. Right? This is your gradient. Right? Again, where should I move is a function of where I was previously in the previous step, plus going in the opposite direction of the gradient for a step size alpha. Right? Going in the opposite direction. This is the gradient and this is going in the opposite direction of the gradient. How much should I go? Step size alpha. This is your steepest gradient descent. Okay? That is wk plus 2 alpha sk ek. Okay? But note, now you have to choose a pretty small alpha. Why? Because you made this approximation, right? That's an approximation. So basically, the gradient that you're calculating is not precise, right? Because the ideal gradient should have been RS and RDS, but you're getting it, you're doing some approximation here. So because of that, you need to be careful. So you choose a small alpha. Since you made the approximation of the expectation with the instant value, right? You made E SKDK, you made that as only SKDK. For that, you want to choose small alpha. Because if this approximation is wrong, and if the gradient is pointing in the wrong direction because of the approximation, and if a large alpha, you'll end up going in the wrong direction. Okay, very good. So once WK is known, okay, by the way, let me first say, this is the end. Because now you have this gradient descent. You keep applying WK plus 1 until when do you stop? Guys, when do you stop?
Is it when EK is equal to 0?
Okay, that's one way to say EK is equal to 0. Yeah, actually, that's a good way to say it. That's easier. When EK equals 0, I'll stop. Very good. Make sense? But there's noise and all of that. So EK is not going to be 0. When you say when EK is less than some epsilon, I'll stop. Right? Now, here is an important one. Let me ask this question and try to answer me, try to think and answer me. This guy is saying, hello, how are you? Okay, he's speaking. So dk is constantly changing. My question to you is, this W star that I have figured out from the adaptive filter, should this W star constantly change because dk is constantly changing and even S is constantly changing? Or even Sk is constantly changing, dk is constantly changing, should Wk constantly change?
I think you only need to change, like, it's not based on the signal, but based on like the channel. So like basically like if the person moves, I think.
Correct. Absolutely correct. W turns out to be this. Right? You figured out the channel. Now, once you figured out the channel, what W is essentially doing over here is that this is G inverse H. Let me write that. Minus W equals minus G inverse H. Right? So look, dk is essentially H of X. Right? Now, WTS is nothing but minus G inverse H S. Right? Once W has converged to minus G inverse H. So minus G inverse H and now times S. Now S is nothing but, what is S, guys? It with respect to X. D is Hx, or we should say H convolved with X. Agree? So what is S? What convolved with X?
Is it G convolved with X?
G convolved with X. Right? So, sorry, let me just clear this once. This G inverse is going to cancel this G. By the way, A convolved with B is the same as B convolved with A. So this G inverse is going to cancel this. So what remains? So what is WTS now? Make sense? What is bugging you guys? I can feel a silence. Anything bugging you? Okay. So then look, it's minus H convolved with X. This is H convolved with X. I'm canceling. I don't care what the X is actually. Right? Whatever X is doesn't matter. If I've converged onto this, I will keep canceling the sound unless this guy moves, or maybe some environment object moves, because there is multipath over here. So if the environment person moves or some chair or table moves, then of course the H and G will change. But as long as H and G does not change, W can stay fixed. And whatever the person is saying, hello, how are you? W will keep canceling. The DSP will keep canceling the signal. Very good. Okay. So this is the last thing I wanted to write, is that once WK is known, any signal X can be canceled at the microphone, at the feedback microphone, unless what? The channels H or G change. Okay. This whole thing that we discussed is called active noise cancellation. So this is what your headphones are essentially doing when they try to cancel the sound.
Professor, could I ask a question?
Yes, please.
So to, like, let's say the person does move, how is that usually detected? Is it usually detected by sort of like I forgot what the inside ear microphone is called, but is it
feedback microphone?
Does the feedback microphone basically just start picking something up and then it realizes it needs to adjust?
That's a very good question, and I think you almost answered yourself. Can someone add to Lucas's answer? Lucas's question is, if my head moves, how does the DSP readapt? How do I know that something has happened? Okay, the answer is the feedback microphone is constantly giving the EK back to the DSP, constantly, right? If the head is still and the sound source signal is still and the environment is still, the EK is 0, 0, 0, epsilon, epsilon, 0, epsilon, 0. I move my head, EK is 20. DSP says, oh my goodness, right? Again, I mean, DSP is anyway multiplying SK with EK all the time, right? And once the EK is 20, DSP multiplies EK with SK, figures out what is WK plus 1, changes W. Right? That gradient descent is actually continuously happening. So once EK goes up, W shifts. You bring it down. You bring down EK.
Okay, that makes sense. So, and anyways, I guess it's doing it all the time.
All the time, yeah, all the time. But you could put some logic in there saying, look, if EK is less than epsilon, don't bother. You can say that, right? And yeah, like only when EK is greater than 10, then only restart the gradient descent process.
Okay, cool. Thank you.
Okay, any other questions? Very good. If not, now let's look at some fun application. Fun application of noise cancellation. Perfect. Oh, very good. I just don't know how to undo. Hey, anyone knows how to undo on an iPad? Okay, I'll just scratch things off. I'll try to be neat. Okay, so now we are kind of back into mobile computing. We were doing a bit of math, but we are now back into mobile computing, and we'll see if we bring IoT to ANC, are there interesting things we can do? Okay, let's get started. Okay, so noise is everywhere. Right? This is why the noise cancellation industry is so liked, right? This is a presentation slides that some of my students created. So there are some nice pictures. So co-workers chatting over the phone, construction sites near your classroom, this 5 a.m. guy who wakes up and starts lawn mowing, busy streets in big cities. There's lots of noise everywhere. And today's solution is these headphones, right? Now, this project that I'm going to talk about essentially tries to do two things. One is it either tries to cancel noise better for the same headphones that are available today, or it tries to create open ear headphones, but that will achieve comparable performance as of headphones today. Right? So if you block your ear, you either do better noise cancellation, or if you do not block your ear and keep your ear open, then you do comparable noise cancellation as today's headphones. Is that clear? So the goal of the project is either do this or do this. Okay, good. And the core idea is basically we'll combine wireless networking with noise cancellation. Okay, and the system is called Mute. Very good. So here is the key idea. If you get this key idea, you've gotten the fun part of it. Okay, here's the fun part. Let's say Alice is sitting and reading a book in her office in grad school or in undergraduate, and some people are talking very loudly in the corridor, and Alice is getting disturbed. So this Mute project says, here is one solution. The solution is Alice puts a little IoT device on her door, and this IoT device essentially has a microphone and a wireless transmitter. Okay. And what is the IoT relay's job? This device's job is whenever sound arrives from these guys to this device, to this green device, the green device's microphone hears that sound and then relays that sound over a wireless packet. Right? So this you can think of as maybe Bluetooth. So the Bluetooth data packet essentially contains the sound that these guys are saying, which is like, hey, how are you? Hey, how's life? Right? This, hey, how is life? This sound can be very much sent like a Bluetooth packet, right? I mean, that's what your earphone gets from your smartphone when you're listening to a music. So, but you send that over BLE, and now Alice's headphone also has a wireless RF receiver, a BLE receiver, let's say. It gets this packet and pulls out the data from that wireless BLE packet, and that data is the sound that those guys are saying, talking, right? Hey, how's life? But here is the main idea. Wireless signals travel 1,000,000 times faster than sound, right? Which means Alice's receiver got to know the future, even though the future is taking its own sweet time to come to Alice, right? Because these sound signals are actually coming, but Alice has already seen the sound signal which have not yet arrived to Alice. Or rather, Alice's earphone has already seen that sound signal. So in some sense, because of this wireless relay, Alice's device gets a look ahead into the future. And this look ahead is essentially a time cushion. I'm seeing more of the signal beforehand, and I can utilize this look ahead for useful noise cancellation. Someone tell me if this is clear or if there's a question here. Of course, the assumption we've made is this relay has to be between the sound source and Alice. If the relay is behind Alice, where somewhere over here, then this won't work. Because by the time the sound arrives at the relay, the sound has also arrived at Alice's headphone. Right? So the assumption is the relay has to be between the sound source and Alice. Right? So here is a basic analogy. When there's a lightning and a thunder, you see the lightning first, and you can see the lightning and basically close your ears because light is traveling so much faster than sound. Right? Can we do similar stuff in noise cancellation? And again, guys, observe classical signal processing research would only worry about noise cancellation. But once you bring in wireless, IoT, other kinds of Lego blocks to the table, you can create new kind of technologies and new kind of ideas and systems and algorithms based on this. Very good. So the question is, can we leverage this look ahead for different gains in terms of noise cancellation? Okay. And we'll talk about 3 different gains. One is timing gain, which is wideband noise cancellation. One is signal processing gain, which is where we are going to look at that RS, RSD, those covariance matrices, and we try to see if there's some gain that we can get there. I hope you're getting an intuition of why, because that expected value, we made it instantaneous. But if I have a look ahead into the future, maybe I can do better stuff. Right? And then another gain is an application specific gain where I can maybe do sound source profiling, meaning suppose Alice and Bob are taking turns and talking. I would know ahead of time when Alice stopped talking and when Bob has started talking. So maybe I can switch my filters in my headphone based on, oh, I know Alice is going to stop in another second and Bob is going to start right after Alice. So let me switch my filters because Bob's channel and Alice's channel, those H and G are different, right? So I can switch between my W vectors based on who's going to start talking right now. And I can do it predictively as opposed to, I think Alice is talking and then Bob starts and my EK is very high because Bob's channel is very different from Alice's channel. And then I have to do gradient descent to come down again. Right? Today's noise cancellation headphones, if 2 people are talking and their sounds are coming, when Alice is, well, let's not call it Alice because Alice is the receiver. Let's say Bob and Susan are talking. When Bob is talking, your headphones H and G have done gradient descent and converged to some value, which is a function of Bob's channel. But once Susan starts talking, the channel has changed. So now your noise cancellation headphone has to redo gradient descent to find out the new W vector, right? But when it's redoing this new estimation, your noise cancellation is not perfect. Okay? But if you have look ahead into the future, you can do better stuff. Any questions thus far? Okay, good. So let's start with this wideband cancellation. What's inside a noise headphone? Now you know this reasonably well. The signal comes in over a channel H, over a channel G. The signal also comes to the feedback microphone over a channel H. The feedback microphone gives this error feedback EK. We talked about all of this now. DSP's job is to figure out this W vector. Make sense? This is exactly what we saw. The question is, how do they perform today? This business. This is exactly what is happening in today's noise cancellation headphones. How do they perform? Okay. So this is Bose's QC35, which is pretty much the state of the art, the best noise cancellation headphone you have today. And if you look at the noise cancellation performance, this is what the graph looks like. Y-axis or this axis, the lower you go, the better is the cancellation. Okay, so this is 0 dB, meaning nothing is getting canceled. Minus 10 dB means reasonable amount is getting canceled. Minus 30 dB means a lot is getting canceled. Okay. X-axis is frequency. Okay. Remember sound, human voice, the bandwidth is maybe 0 to 14, 0, actually not even 14, 8 kilohertz. Okay. So human voice is generally between 0 to 8 kilohertz. So if you look at frequency, turns out not only Bose, all noise cancellation headphones today cancel up till around 1 kilohertz. The rest of the frequencies above 1 kilohertz don't get cancelled. But you say, hey, that's surprising, because when I put on my headphone, it seems pretty good, right? How come it's only canceling till 1 kilohertz and the rest of it is still going through my headphone? Well, this is where this material, the sponge that is on your headphone, plays a very crucial role. Okay. And this is why it is difficult to design a noise cancellation headphone that is hollow, meaning that's passed through. That's very hard. Because for this part of the frequency spectrum, you need that sponge. And by the way, all these companies have invested a lot of research on that sponge, because the sponge has to be lightweight, the sponge has to absorb sound, the sponge has to operate over this whole frequency from 1 kilohertz to 8 kilohertz. So it's a wideband sponge. All of these have to happen. And the sponge, therefore, is manufacturing the sponge is not easy. There's a lot of material science research that has gone in. But once you put that correct sponge in place, this is what the noise cancellation performance looks like, which is, wow, pretty good. Right? Because in all these frequencies, this is the sponge. And this part, 1 kilohertz, is basically ANC, active noise cancellation, plus sponge. Questions? Good.
Do these sponges act more like a low pass filter?
The sponges why low pass filter, Eric?
Oh, because I think one of my previous professors they were talking like how walls acted like a low pass filter. So I was just wondering if this is like similar to like that.
Yeah, but I mean, low pass filter is where the high frequency sounds will not go through, right? But here, even the lower frequency sounds are not going through very well. So the sponge is more of an absorber. Okay. And I do not know material science very well, but one of the possibilities is that if you think of it inside the sponge, the sound may get scattered in such a way that they cancel each other. Right? The sound is kind of scattering, right, in all random ways, and they may cancel each other. Okay, but don't quote me on that. I do not know this, how the material treats the sound very well.
Yeah, that's fine. I was just curious.
Yeah. Great.
How is the performance of like just the sponge versus active noise cancellation?
Oh, that will be like you subtract the red curve from the green curve.
Got it. Okay.
Right. So maybe the sponge will behave like this over here, and then it will go like that. So the sponge's cancellation in this part is not super good, but that's okay, because your noise cancellation, electronics is taking care of that frequency band. But this frequency band, your electronics is not taking good care of it. So you let the sponge kick in. Okay. So the question is, why does noise cancellation not work at higher frequencies? Okay. So let's look into that headphone again. So here is a timing diagram. Okay. Time is flowing in the downward direction. Okay. Now look, let's say that the sound is coming from the user, from that corridor speaker, loud person, all the way to your ears. And time is going in the downward direction. So this time is T1, this time is T2, and so on. Agreed? Great. Now, your reference microphone is getting the sound at T1, right? And tell me, the reference microphone gives the signal to DSP, and the DSP has to compute WT or W, that vector, and give that W transpose times S to that speaker, right? And the speaker has to play WTS. Do you all agree? Do you all agree? My question now is, at what time should the speaker play W transpose S?
So assuming we can calculate it within like the time, we basically want to delay by the amount of delay, like the difference in distance from the reference mic to the feedback mic, right?
Correct.
And like,
So how much is that? You're right, Lucas.
right?
So tell me, right? This is the actual sound that is coming in, flowing through your headphone and getting into the ear. Your reference microphone captured the sound, and now it needs to, now the DSP needs to compute the anti-noise. This is called the anti-noise. And the DSP needs to play the anti-noise in a way that the anti-noise will cancel the actual noise. So your reference microphone gets it at T1, let's say instantaneously gives it to the DSP. This is S. Please pay attention. S has to give it to the noise, to the anti-noise speaker, and the anti-noise speaker has to play. Let's say the anti-noise speaker can play immediately at the very instant when it gets the WTS sound. So how much time does the DSP have to compute WT?
Is it like speed of sound over 1 centimeter?
Correct, exactly. Rather 1 centimeter over divided by the speed of sound.
That's right, yeah.
Right? And in this figure, how much is that? In terms of T1, T2?
30 microseconds.
30 microseconds, that's true. It's T2 minus T1. Right? So the DSP gets the sound signal here. This is when the DSP gets the sound signal in time, right? And the DSP has this much time to compute W. Compute W in that much time. And now, once you've computed W, you give it to the noise, the anti-noise speaker. This is WTS. And the anti-noise speaker should play the anti-noise sound exactly at time T2, so that the actual sound going in and the anti-noise speaker sound, they are kind of going together. Right? So this, in some sense, you should think of the black line as DK and the red one as WTS. So if WTS and DK both arrive at the feedback microphone, then your EK should be 0. Right? And the DK and the WTS both will finally arrive at the eardrum, and hopefully they'll also be 0. So the time budget that the DSP has is T2 minus T1, and T2 minus T1 is basically 1 centimeter, given that this is pretty much 1 centimeter, divided by 340 meters per second. That's the time budget it has. Very small. Okay? Around 30 microseconds. This is why many of these headphones, earbuds, they've all pushed the DSP's job into analog. You don't want to spend any time in sampling, ADC, all of that. Right? So this is not a hardware class, so you're not going to get into that. But only thing to remember is analog means you can do things faster. Right? So most of these things would happen in analog. Very good. Now, if the DSP gets late, misses the deadline is T2, but it misses the deadline and it finishes the computation at T3 and then plays the anti-noise. What happens? What happens is the actual sound signal and the anti-noise signal are now at a phase lag. Do you agree? Right?
Yeah, in the worst case, it would amplify the noise, wouldn't it?
Yeah, exactly. If the phase lag is, suppose this is a sinusoidal signal. If the phase lag is pi, you have if the phase lag is pi, then what happens? You've canceled the signal. If the phase lag is 2 pi, you've amplified the signal. Right? You definitely don't want to amplify. Right? So now, so the bottom line is, if you're delayed, you incur a phase lag, and because of the phase lag, your cancellation is going to degrade. You agree? So delay, or rather missing deadline, equates to worse or proportionally worse cancellation. That you agree? Okay, guys, now tell me, will all frequencies have the same degradation in cancellation? In particular, what is the difference between low frequency and high frequency? Low frequency is like that, and high frequency is like that. So now tell me, if I am delayed by some time, let's say tau, I've missed the deadline by some time tau. Okay. How much phase lag am I going to see with the low frequencies and how much phase lag with the high frequencies? Or in other words, should I see more phase lag with the low frequency or more phase lag with the high frequency?
It'd be much worse with the high frequency.
Much worse with the high frequency.
Yeah.
Right? So higher the frequency, a little bit of delay, a little bit of missing the deadline has a bigger penalty. Right? So this is what it says. Look, let's say this orange is the anti-noise and the noise is the blue. If you have missed the deadline by a little bit, your residual error, which is EK, is this signal. This is for a lower frequency. But now look at a high frequency, and if you miss the deadline by that same amount, the same amount you're missing, the difference is much larger. You're almost starting to amplify now. Right? This EK is much worse. So lower frequencies, you are not too bad. Higher frequencies, you're in a bad situation. I hope now this explains why lower frequencies you cancel reasonably well, higher frequencies things get bad. Questions?
On the last slide, your like actual like mathematical phase measurement, it would also be bigger for higher frequency, right? Like it's not just
the phase measurement, the phase difference would be bigger for higher frequencies.
Okay. Okay. Oh, and that makes sense because this is kind of like why in FFT in frequency domain you have to adjust like if a certain time delay.
Correct. Correct. You have to multiply that e to the power j. That frequency has to be there.
Okay, so this is like the same thing, kind of.
Exactly.
Okay, cool. Thanks.
Exactly. Okay. So this is why today's headphones have this problem. But now let's see what happens if you put mute, that relay into the environment. Okay. So what is mute doing? Mute can be thought of as, remember, I'm putting a relay closer to the source, right? So I can think of that as I take the reference microphone out of my headphone and I push it closer to the sound source, right? And then what happens? The sound arrives at time t1 at the relay, and the relay forwards that over wireless, ignore this. It forwards over wireless to the DSP. And that is almost instantaneous relative to the speed of sound, right? Light travels 1,000,000 times faster than sound. So now how much time does the DSP have? The DSP has this distance. Let's say this is 1 meter. 1 meter divided by 340 meters per second, which is much more than 1 centimeter divided by 340 meters per second, right? So now the DSP has this whole time to compute its WT. Right? Or WTS. And therefore, it can very much not miss the deadline. And therefore, the anti-noise and the sound would go together. It'll cancel across the whole bandwidth. Make sense? Very good. That was wideband cancellation. Maybe I should just talk about these two at an intuitive level. Because you see the future signals, right? Now your approximation of SK transpose or SK-DK, right? You don't need to do that because you know your SK in the future, you know your DK in the future. You can compute those covariances much better. You agree? So that's a much more fundamental gain because I see the future, I can compute these covariances much better. Okay? So that way the filtering becomes much more, your W estimate becomes much better. Because you don't have to do that approximation so much. In fact, the further you push the relay away from you, the more look ahead you have, right? So that's the signal processing gain. And finally, there's a sound source profiling gain. Let's quickly look at that. Again, you can feel free to look at the slides. You'll understand it completely because we've talked about everything. This F inverse G is what we talked about. Okay. And there's a gain which is sound source profiling, which is, let's say, okay, I called this person Alice and this person Bob. Let's say Alice and Bob are talking and you have your headphones on. So when Alice's sound is coming, your headphone did gradient descent. This is basically the signal EK, right? The signal EK was large, but because of gradient descent, it came and became small. Guys, are you all with me? Can you guys give me a reaction? Maybe a thumbs up. That EK goes up. Okay. Now suppose Bob starts talking. What will happen to EK? What will happen to this graph? What will happen to this graph? The black graph. Anthony.
EK will go up again because the channels are different.
The channels are different. EK will go up again, and then again it would converge. Why will it converge? Because again that gradient descent will kick in. Okay. So once Bob starts, EK grows, and again EK converges. But when this EK grows, you are actually going to hear Bob's voice, and then it is going to decay down. Right? Actually, you may not notice it because your sponge is doing most of the job. Right? Your sponge doesn't care about any gradient descent, right? So this is what is happening constantly when people are taking turns and talking. You don't want this to happen. So what can you do? Oh, now look, with look ahead, let's say you figured out a fingerprint for Alice and a fingerprint for Bob, right? Because if you look at the frequency domain signals of Alice, Alice has a shrill voice. So this is Alice, this is Bob. Bob has a bass voice. So this is Bob's frequency response. Right? Voice ID, all your Siri and all of these, they do this voice fingerprinting, right? They basically look at the characteristics of the voice. So Bob has this profile and Alice might have this profile. Because maybe Alice has a more higher pitched voice. Females have a higher pitched voice. So you figured out from the profile which is Alice's signature and which is Bob's signature. And now you have the look ahead. So from the look ahead, you basically, you'd say, what signature does this look ahead signal have? And you say, oh, this signal is actually Bob's, right? So then you say, I know what Bob's WT is, right? So this time over here, you figured out Alice's WT. And then over here, you know that Bob's signal is coming. So you don't do gradient descent once again. At that time when Bob's signal arrived, you just apply Bob's WT that you had estimated beforehand, right? And as a result of that, now Bob's signal does not create that spike in EK, it stays small, right? And you can do that only because you are able to see the future and you know when the switch between Alice and Bob is going to happen. Very good. So now the rest of it is this implementation and evaluation of this whole system. This was done in UIUC. You are going to read the paper and review the paper. And it turns out that with mute, this is the performance. This is mute when you use Bose's headphone, but you run the mute algorithm and not Bose's ANC algorithm. Right? So you're blocking the ear, but instead of running gradient descent with the Bose's algorithm, you're running all these advantages that mute gives you, right? And that's the gain. Green is Bose and this is mute. But then you can say, okay, look, if I did not have the sponge, how good will I be? Right? Mute will allow you to do good cancellation. So why not take out the sponge? You lose something, of course. So this red one is what is called mute hollow, meaning without the sponge, what will you get? And it turns out that mute hollow is reasonable. It's a little bit worse than Bose with the sponge, right? So mute no sponge is a slightly worse than Bose with sponge, and mute with sponge is much better than Bose with sponge. Okay. So that's basically the high level idea. And again, you're going to look at these slides, you're going to look at the paper, and that would give you a good sense about how mute actually helps. But again, if you've understood adaptive filtering thus far, you've understood everything. Questions?
So it seems like this one constraint with mute is this hardware relay that needs to be at the right position somewhere in the room, right?
Correct. The relay needs to be at the right position. Okay. So if this is Alice, if this is Alice sitting at her chair, and if this is the sound source, if this is the sound source talking over here, right? And there's a earphone that Alice is wearing, or a headphone. The relay needs to be here. But you don't know where the sound source is, right? Someone behind Alice could also be talking. So one question is, where all do you put a relay to ensure that any sound source will be further away than the relay, and therefore you can do mute? In fact, this is your homework question. Question is, how many relays do you need to put around you so that any sound source outside that circle would be further out compared to the relay? Right? So for example, right, imagine this relay, the one that I shaded green. The sound source for mute, the sound would go here and then would come here. That's the path the sound would take. Versus the direct sound would come like that. Right? So if you move the relay too much towards here, that reflected or that relayed path might become longer than the direct path. Right? So the question is, there is a number of relays, and you can do this through geometry. There's a number of relays that you can put, a maximum number of relays, a minimum number of relays that you can put so that the relayed path from any sound source will be shorter than the direct path.
Does that depend on circle radius or no? Like distance from person to relay?
No, the number does not depend on the circular radius.
Oh, okay.
Right. Okay, good. Any other questions? What if everyone just wears a mic that broadcasts themselves with a radius? That's exactly right, Eric. In fact, what you'll read in the paper is, if tomorrow the lawnmower has a relay, right? If the lawnmower has a relay, then the lawnmower can take its own sound and relay it. If the drill has a relay, it can take its own sound and relay it. And if you have a earphone that's receiving these sounds from the sound sources, that's a huge look ahead, right? Because you know what that sound is immediately, right? So definitely you can do these things. Yeah, $1 million idea. So if you want to run startups, you're welcome to. Okay, guys.
Honestly, wouldn't even be in the top 10 weirdest startup ideas.
Say that again.
Wouldn't even make it into the top 10, top 50 worst startup ideas.
Wouldn't, right?
No. I've seen far worse.
Okay, good. So that's where we'll stop today. In fact, there are other ideas over here in the paper that you'll see, right? What if your Alexa became the relay, right? Your Alexa could basically relay the sound to you so that you can do the cancellation, right? So there are all kinds of ideas in the paper. Take a look at it. Okay, with that, we'll move on to the last part, which is midterm review. And let's quickly go through this part, okay? Next 15 minutes, 20 minutes. Okay, not much to be said. Wednesday, April 21st, online Zoom. Please register with CBTF. Okay, CBTF needs to know who all are going to give the exam and how many people and so forth. And also check timing. I believe it's in the evening. Okay, so check the timing. I think also there's a conflict time. Guys, there might be people who will take the exam at the conflict time, which will be the next day morning, because some people are in Asia and Europe and other places. So please don't talk to anyone else about the question. Right? To your friend, please don't talk to anyone else. Okay. Duration of the exam is 1 hour 20 minutes. You'll have 1 hour 50 minutes for the exam. My feeling is you'll be able to finish this well in time and upload it within 1 hour 50 minutes. This will be all pen and paper. You're going to take pictures and upload into Gradescope. Okay. CBTF exams, I hope all of you have given some CBTF exam by now. You'll be required to keep a laptop camera so that CBTF proctors can see basically what you are doing. Okay. Difficulty level is not hard. I would say it is easier than the homeworks that you've been solving. Cheat sheet, 1 A4 size sheet, front and back. Syllabus, everything covered till today, April 14th. Today is April 14th, yeah, including today's lecture. Okay, but of course, optimization and acoustics, there's going to be less content, less questions from the later, the optimization and acoustic cancellation part. Approximate exam format, around 5 questions, I think 5 questions. First one is state true and false with justification. Concise justification is key. Okay. I might say that if you do not know, if you keep it blank, you get a point, or if you get the justification wrong, you might get a negative point. I might have a negative scoring to prevent you from throwing a kitchen sink at the answer. Right? Question 2 will be around foundations, mostly math. Okay, so your linear algebra, your signal processing, and a little bit of probability. And question 3, 4, 5 are basically topic specific questions. You may need to argue in favor or against, short solve problems, complete sentences, detect flaws in a pseudocode, give counterexamples. Approximate exam format, questions will not require you to remember any details. Okay, such as no one's going to ask, how many unknowns are there in the arm motion model in Armtrack? No one's going to ask you any of that, right? What was the localization error in radar paper? Or what are the features used in unlock? None of those are going to be asked. All the questions will be very much conceptual and very similar to homework problems, right? Not the difficult homework problems, but the conceptual homework problems. In fact, the homework 3 that you have is a very good preparation in addition to the math foundations, which I hope you have. Homework 3 is what I was thinking of midterm questions. I was saying, okay, these questions I won't put in midterm, let me put them in homework 3. Okay. So focus on understanding math foundations and physical meaning of the math. Understand how math applies to different applications. Think about why a particular technique is or is not the correct approach. What could have been other ways to solve the same problem? Okay. These are, generic, vague, but I think the best advice I can give is homework 1, 2, 3. Okay. And given that you've done MPs, my feeling is you've had a first-hand experience of playing with these signals, understanding what is happening. So homework 1, 2, 3, and given that you've all done the MPs, I think is pretty good preparation. Maybe working in pairs is a good idea, where you can ask questions to this other person and say, why should I do this way? Or in other words, teaching an particular concept or an idea to another person is going to give you clarity. Right? And the other person could ask you. So one could teach GPS to this guy, and the other guy could teach indoor Wi-Fi localization to this guy.
Professor, I had a quick question.
Yes.
Were you planning on giving solutions for the homework 1, 2, 3, or before? No, sorry.
No, because that we are not planning, because homework 1, 2, 3 is due after. But at the end of next class, I'm happy to stay back as long as necessary, so that we can, if there are questions that you have in mind, I can discuss those with you.
Yeah, sure.
Related to homework 3. Okay. So homework 3 questions are here. I definitely want you to go through homework 3 carefully. So here are some examples. A signal that is below the noise floor, that is, amplitude of the signal is less than the noise amplitude, cannot be detected through cross correlation. True or false? Maybe this is among the more difficult ones, but here is the idea. There is a signal. This is the signal. Let me make a copy of it. And there is noise that is getting, when the signal is arriving, let's say the GPS signal is arriving at your receiver, and there's noise, of course, that's getting added. So noise gets added on top of this. Noise can be positive or negative, right? So the net signal that you get is or maybe that last one would get cancelled, so it would be like a little bit. This one would be like that. 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 This one is going to be 0. This one is going to be almost 0. This one is going to be large. This one is going to be large. This. Guys, does that make sense? Black is the net signal that you're going to get. And the question is, this black signal is the GPS signal that you've received, and you know that the GPS transmitter is transmitting this signal. Right? If the blue noise was very small, then you can immediately correlate very well, right? You can take this signal and you can correlate very well. If blue was very small, it's going to nicely correlate, right? And if you move, it's not going to correlate very well. Right? That is what is correlation, right? This is very nice correlation. This is not so good correlation, bad correlation, and so forth. You agree? So if the noise is small, if the blue part is small, then as you shift, you'll suddenly see a big spike, and then everywhere else it will be very small. That's what we talked about in GPS. Right? The question is, if the noise is big, will it still correlate? Can you still detect where the signal is present by moving this back and forth? If the noise amplitude is as big as the signal amplitude. Right? And I won't give away the answer, but I think what you need to think about is, how does this red signal, this template signal, how does that correlate to the blue noise in expectation? Right? So if the blue noise and this red template signal, let's call it this template, because you know that the GPS transmitter is sending this signal, right? Or you know that the Wi-Fi transmitter is sending this signal. So when the template and the blue noise, they're uncorrelated, what does that mean? That on expectation, the product is 0. And typically blue noise is uncorrelated to the template, right? So now, when you have shifted this signal and the signal has perfectly matched with the red part, but is uncorrelated to the blue part, which means on average, that red times the template times blue is 0, but on average, when they are the template times the red, when they are matched up, gets doubled or squared. right? In other words, what you're really looking at is expectation of red plus blue with red. Right? This is what is cross correlation, right? So now red times red template, that is going to get squared at the right shift. An expectation of red times blue times red template, that is where you say, what is the correlation between blue and red template? Are they going up and down at the same time, or are they random? So if the expectation of blue and red template is 0, then what you're left with is expectation of red times red template. That value is large. Right? Good. Let's look at another one. Echoes of the same signal source when arriving at the receiver are correlated. True or false? Echoes of the same signal when arriving at the receiver are correlated. This is a signal. This signal arrives at the receiver from the transmitter on a direct path. So the received signal looks like this. And the echo is basically a reflected path. So in time, if you look at it in time, or maybe, if you look at what the receiver is receiving, the receiver is receiving this signal directly, and then the receiver is copy, and this echo is coming at a later time and getting added up. So the echo, so the question is this echoed signal and this signal correlated? Yes or no? What is correlation? Is there some way where you can shift it so that the signals will match very well? So answer is true or false.
Can we try to answer?
Say it again.
Should we try to answer?
Let's try to answer, yeah.
So I think it's only correlated if the shift is like 2 pi, right?
It's only correlated if the shift is 2 pi. If the shift is not 2 pi, yeah. But correlation means, is there some shift at which the two signals will match up?
Oh, okay. So true.
True. Yeah, I'm not going to say right or wrong, but you can see it from my smile. That's the only information I'll leak. Okay. Let's do another one quickly. Draw an ideal channel impulse response where the channel only has one direct path, the path with the shortest distance, and one echo arriving 10 samples later. Label the diagram clearly. Okay. Guys, channel impulse responses are typically look like this. Again, if I give this question in the midterm, I will give you a drawing of the channel impulse response. Channel impulse response looks like this. This is time. This is amplitude. And this is what channel impulse responses look like. What does this mean? This means that the direct path comes this time later from the transmitter. The first echo comes T1 plus T2, tau 1 plus tau 2 later, right, from the time it was transmitted. From the time you receive the direct path, it comes tau to later. Right? And this value, this amplitude value, often denoted as H1, H2, or sorry, not H1, H0, H0, H1, right? 0 means the direct path, H1 is the first echo, and so on. Because those echoes are getting reflected, the wall absorbs some of that energy. So typically, these echoes are going to be weaker and weaker. Okay? So this is a diagram, a labeled diagram of a channel impulse response. So in this case, you're asked to do something simple, which is the channel has only one direct path with the shortest, direct path is the shortest distance path, and one echo arriving 10 samples later. Label the diagram, and I'll quickly give you a rough hint. Oh, well, you have this direct path, right? You do not know what that value is, but you can call it H0. And then 10 samples later, you get the echo. This is H1. And this is what the channel impulse response looks like. Okay. And now the second question is, this is kind of to get you warmed up. And the second question is, draw an updated CIR with direct path signal plus 3 equally spaced echoes, in which the direct path signal travels through a wall. Okay. And the wall, assume amplitude gets attenuated to 0.5 due to penetration and 0.7 due to each reflection. So now you have to basically say, oh, if I have a channel impulse response, now this first line of sight or the direct path is now going through a wall. So what should happen? If it is going through a wall, this line, what should happen to that line? Should it shift?
Amplitude should be small, right?
The amplitude.
No.
That's right. The amplitude should become smaller. Right? It should not shift in time, right? The line of sight path is when it's coming, the time that it arrived, right? If it came through a direct path, if it came through a wall, then the amplitude goes down. And then if I ask you, true or false, the amplitude of an echo is always smaller than the amplitude of the direct path. Is it true or false?
What if two echoes arrive at the same time and they
No,
arrive?
I'm saying my question is true or false, the amplitude of a single echo is always weaker than the amplitude of the direct path.
False, right?
False.
False. Why is it false?
Like the wall example, because the wall, yeah.
The echo may not go through a wall. The echo will get absorbed by the reflection, but the reflection might absorb less of the energy than the penetration. And this is what this example, this picture, this question is going to push you into understanding. Okay? So these are kind of the conceptual questions you're going to look at. Let's do another one. True, false. The accuracy of delay sum algorithm. You remember delay sum. You have these microphones at which signals are arriving. You shift the phases of the microphone so that all those signals line up together, right? This is the 100-meter sprint example, or the 200-meter sprint example. We said that the athletes are staggered so that when they end, they've all run the same distance, right? That staggering is that phase shift. So the question is, the accuracy of delay sum algorithm is expected to improve with more microphones as receivers. Answer with a mathematical justification. And mathematical justification means you take an equation and you explain that equation. You just don't write only English language. You have to connect your answer to that math. Right? Any intuition what happens with more microphones as receivers?
You have an overdetermined system of equations. It becomes even more overdetermined with more equations.
That's one way of looking at it. True. And therefore you are going to get noise suppression. I think that's one way of looking at it for sure. Right. So in this case, essentially more the microphones, the noises, there will be more samples of noise. And if you have more samples of noise, they're likely to cancel out each other. Right? Look, guys, if I do 3 coin tosses or 4 coin tosses, you may not always get 2 heads, 2 tails. But if I do 1,000 coin tosses, there's a much more chance that you're going to get 500 heads, 500 tails. Right? Or the deviation is going to be much smaller. Right? So if you have more and more noise samples, the noise cancellation is more and more likely. And that's where the gain is going to come from. Complete the sentence. When performing HMM for IMU-based dead reckoning, probability of MK given S1 to K is not equal to probability of MK given SK because probability of a measurement given all the previous states is not equal to probability of this measurement given only the current state when using IMU. When using GPS, probability of MK given S1 to K is equal to probability of MK given SK. This is true for GPS. But for IMU, it's not equal. Why?
Because when you try to integrate using the previous samples, it would have a large deviation due to like noise, right?
I want a more precise answer.
Okay.
Let me do this again. This P MK given SK is basically saying probability of MK given SK, SK minus 1, SK minus 2, all the way to S1. And PMK-SK is saying PMK given just SK. And in GPS, we were saying, or in HMM when we were talking about it, we said, look, once I know SK, I don't care about the previous states. Right? Because if I am taking a GPS measurement, my measurement is going to be a function of only this SK, the current state of the object. If I'm walking in New York, Manhattan, and I come to an intersection and I turn on my GPS measurement is not going to change based on which direction I came to that intersection. But what happens with IMU?
Oh, you can like, there's like bigger probability in like certain directions. You can't just teleport from one location to another, right? Is that?
Remember, IMU is an inertial sensor, right? So my measurement, which is acceleration or gyroscope, my acceleration is a function of, give me what all is it a function of? SK, what else?
SK minus 1 and SK minus 2.
Correct. And what about my gyro? That's a function of? I mean, in this case, SK has to be orientation, right? So gyro is d theta by dt. It's angular velocity.
So just SK minus 1.
Correct. SK minus 1. So that is why when you use an IMU, your state variable, that's why you were saying that state variable wants to be the previous states as well. Last one. Prove that the sum of two convex functions is a convex function. Okay, there's a question. Does this mean that HMM with IMU violates Markovian assumption? No, it's just that the measurement acceleration by design is a function of these three states. Right? The measurement itself is a function of these states. Right? What you can say is once I know these three, then I don't care about the previous ones. Okay? Good question, actually. Does it violate the Markovian assumption? Okay, last one. Prove that sum of two convex function is a convex function. What did we say convex function was? We said f of alpha x plus 1 minus alpha y should be less than or equal to alpha right? This is a convex function because we said this is a chord x, y, right? And then if you take g, that's also a convex function. Right? So now you have to show that if you take sum of two convex functions, right? Imagine hx equals fx plus gx, right? Now you have to basically substitute for x and y. You have to basically substitute and show that when you take this hx, right? Hx, basically you have to show that h of alpha x plus 1 minus alpha y is less than is less than alpha times h of x plus 1 minus alpha times h of y. Okay? And I'm pretty sure you can show that. So that's kind of the flavor of the midterm. Okay. Questions? Again, guys, these are, I would say these are harder because in the midterm, you have to think on the fly. So these are definitely a notch harder than what you should expect in the midterm, but it's good practice. I deliberately wanted to make it one notch higher so that it gives you good practice. Questions, guys? Okay, if not, let me stop the class ends here and office hours begin if you want to stay back and ask. Otherwise, I'll see you on Monday.
Thank you.
Thanks.
All right, Professor, I had a question about number 4 here.
Sure. 444. Yeah.
Here. This is actually something that Liz told us to look over for the MP. Like this question I was asking you about, I think one day.